Hello everyone, now let's look at free response problem 2024 number 5. This is asking us about Le Chatelier's principle, and let's look at a gas phase reaction, a simple combination reaction. 1 mole of hydrogen gas is combining with 1 mole of iodine gas. Hydrogen is a gas in room temperature and 1 atm pressure, but iodine is a solid, so we need to heat it up iodine to make it into iodine gas. Both of them, they are diatomic molecules. Hydrogen, hydrogen combined by single covalent bond, and iodine, iodine, it is also combined by single covalent bond, but iodine has 3 lone pairs because iodine is a halogen, and they are making 2 moles of hydrogen iodide. So 2 moles of hydrogen iodide making, and delta H is negative 12 kilojoules per mole. So this is exothermic reaction. The negative sign meaning heat is coming out from these chemical reactions. Okay, write the expression of K sub C based upon the concentration. Let's write the equilibrium constant. So equilibrium constant is based upon the concentration. So K sub C is hydrogen iodide concentration. We are using the coefficient as a power to the second power divided by hydrogen ion concentration. I'm not ion, hydrogen concentration, gas concentration, and iodine gas concentration. And remember at equilibrium. Okay, reaction quotient and equilibrium constant has same expression, but the difference is equilibrium constant is at equilibrium state. That's the main difference. And equilibrium constant is a constant, doesn't change at all as long as the temperature is set. When the temperature is changing, equilibrium constant is also changing. Okay, and let's look at this diagram. Hydrogen gas and iodine gas are added to an empty container and allowed to react. At a certain time, the reaction quotient becomes 0.67. Draw the number of hydrogen iodide gas molecules to complete the diagram. Let's write the expression Q sub C is equal to the hydrogen iodide concentration square divided by hydrogen, let me erase it, hydrogen concentration, and multiply by iodide concentration. Okay, so the power is 2 and 1 and 1, and this is mole number. So this is mole number of hydrogen iodide over volume square divided by mole number of hydrogen gas over volume. That's the definition of molarity. Molarity is mole divided by volume, and mole number of iodine volume. So this one is mole number of hydrogen iodide square divided by volume square, and divided by mole number of hydrogen gas times mole number of iodine gas divided by volume square. Here's a volume. So then volume square cancels out. It is simply mole number ratio. And mole number ratio is same as number of particles, Avogadro's number. So then we can simply substitute number, not the mole number, into this expression. Now let's look at the number of hydrogen iodide gas is unknown, and number of particles. Hydrogen gas 3 particles, and iodine 2 particles. And then it says that the value is 0.67 at this time. And then let's rearrange the equation to calculate it. So it is 6, this is 6. Let's multiply 6 on both sides. It is 6 times 0.67, which is 4. And then when you take a square root on both sides, we find that number of hydrogen iodide gas is 2. So then simply draw 2. So hydrogen iodide right there, and hydrogen, and iodide right there, hydrogen. That will be making complete view of at this time, representing the proper diagram of concentration. Okay, hypothesize the experimental change has occurred, and in the rigid container at time t for the change, assume that the student did not add any hydrogen iodide to the system. Okay, so let's get the difference of time. Initially, it was changing, reaction was occurring, and it was reaching, the moles doesn't change anymore. So in this region, the equilibrium has established. Now at a certain time t, a certain disturbance occurred to the system, and it is now into non-equilibrium system, and which is second equilibrium. Another equilibrium is reached right there, the moles of hydrogen iodide. So from first equilibrium, let me set equilibrium 1 to equilibrium 2, the system has changed, and what kind of action might have affecting this change. Okay, so let's write the equation. Look at the equation again. Hydrogen gas and iodine gas, and two moles of hydrogen iodide generated. It is exothermic reaction. To represent this one properly, let's write the heat. This is exothermic. Let's write the heat on the product side, 12.19 kilojoules of energy per mole of chemical reaction. Okay, so in order to make the reaction going to the product side, we need to get rid of the heat. Heat is generated. We need to get rid of the products. And then the equilibrium will be moving toward the product side. Or we are adding more of either of these reactants. Then the reaction will be moving toward the product side. And making the more moles of the product, hydrogen iodide. So first method will be cool the reactor, cooling effect, and take off the heat, eliminate heat from the reactor. Then because this is exothermic reaction, the reaction will be moving toward the product side. Or second, add more reactants, especially the limiting reactants. It doesn't specify how much of the hydrogen gas, iodine gas added. It's not specified. So add more limiting reactants will be making the reaction produce more. Okay. After equilibrium is established, the mixture is transferred to a large container at constant temperature. As a result, the number of moles of hydrogen iodide gas increase, decrease, or remain the same, justify. All right. So then as I drew before, this one is first hydrogen iodide square concentration and hydrogen times iodide gas concentration, and this one is simply volume cancelled out. It is mole number square divided by mole number of hydrogen gas and mole number iodide gas. Volume disappeared. Here, volume of the container disappeared. Container cancelled out. So because the volume does not appear in the case of C expression, then volume, when you make this one into a bigger container, it doesn't change. So will not change. The mole number will not be changing. And the same. The the amount of hydrogen iodide will remain the same. Okay, in this part we saw the Le Chatelier's principle, how to apply the concept. When the system is now triggered some kind of change, the system is moving to minimize, offset the change. And then like this concept is very important I'm currently teaching organic chemistry. In organic chemistry, we are using Many systems are equilibrium. To make more of products, we are taking the products off or heat off, and then the reaction will be moving toward more, making more of the products. This concept is very important. So let's have a clear understanding of Le Chatelier's principle. And thank you everyone for watching this video. I'll be seeing you in next video.